Chapter 6, Neutralizing the Threat of Acid Rain, Part 2. In this lecture, we'll be talking about ocean acidification and the pH of rain. Please watch a video regarding ocean acidification. What we want to understand is if rainwater is naturally acidic, even neutral rainwater not influenced by acid rain has a pH of about 6, with neutral water being a pH of 7, why is the ocean water slightly basic with a pH of 8.2? Well, ocean water, or the oceans themselves, are saturated with calcium carbonate. This would have arisen through deposits in the ground. And calcium carbonate is a weak base. So there are three chemical species responsible for maintaining ocean pH. And it's some of these chemical species that are responsible for the pH of your blood as well. So the carbonate ion on the left, you could see, has a charge of 2-, which allows it to pull acidic protons out of water, decreasing the pH. And this ion is formed when calcium carbonate dissociates. A saturated solution means there's so much of it in solution that it begins to precipitate out. If you recall our discussion of concentration and molarity with the gold chloride, when we added enough gold chloride, it began to settle on the bottom. So there's a lot of carbonate in the ocean. When it picks up a hydrogen atom, it becomes the bicarbonate ion. And it can also pick up an additional one and become carbonic acid. But since this is an acid, it will lose a proton readily and form the bicarbonate ion again. And what we'll look at later on is how dissolving carbon dioxide in water due to increased production by industrial and transportation sources can cause an increase in carbonic acid in the oceans, which then increases the number of protons and therefore acidifies the ocean, decreasing the pH. So again, the acidification occurs by lowering the pH. And this can occur by increasing carbon dioxide. How does this affect the availability of the carbonate polyatomic ion, which is needed for animal shells and coral? Well, if we produce carbonic acid from carbon dioxide, that H+ can then react with the carbonate polyatomic ion, causing it to no longer be available for marine life. Marine life can only use the carbonate polyatomic ion in incorporating it into its shells. They cannot use the bicarbonate ion. So what happens then is the shells, which are made up of calcium carbonate, actually begin to dissolve. The effect isn't so dramatic that they begin to disappear, but they have a harder time making shells with adequate thickness to protect themselves. And you also see the shifting of pH actually influence the health of the animals and the health of coral reefs. So in order to replenish the carbonate ion concentration, we see more of the solid calcium carbonate dissolving. So this picture shows the carbonate cycle in the ocean nicely. We have the saturated calcium carbonate on the bottom here, and that can be used by coral and shellfish, and that's actually in equilibrium with the dissociated ions, What equilibrium means is that you have the calcium ions and the carbonate ions, and occasionally they combine and form solid calcium carbonate, and then the solid calcium carbonate will dissociate into ions, and it's a dynamic shifting process. It goes back and forth and back and forth. And that carbonate, when it is dissociated from the calcium carbonate, can pick up H plus ions, forming the bicarbonate ion and keeping the pH of the ocean slightly alkaline. But what can happen is excess CO2, upon reacting with water, forms carbonic acid. And this carbonic acid contributes protons into the ocean, acidifying the ocean. Let's take a look at the pH of rain. So neutral rainwater is about pH 6, but recently the average pH in the United States, or at least in the last 100 years, has dropped down to about pH 5.7. And if you could look here on the East Coast, you can see that the average pH of the rain is much lower. Why do you think that is? There's Portland over there. We have slightly acidic, maybe a bit below the average. Well, the reason being is unfortunately the air currents are such that air masses tend to move from the west coast to the east coast, pulling any pollution produced on the west coast and central U.S. over to the east coast. And we're going to talk about now how the pollution actually acidifies the rain. Just like carbon dioxide can dissolve in the ocean to produce carbonic acid, that can also occur in clouds or in moisture. And again, when that rain falls, that carbonic acid can produce H plus ions. And this will lower the pH from about 6 to 5.3. Additionally, the majority of the acidification of rain tends to come from SOx and NOx compounds, SOx and NOx compounds. We've talked about this before. We know that sulfur dioxide and nitrogen dioxides can be produced during combustion reactions. So when you get combustion of coal, releasing sulfur and sulfur oxide into the atmosphere, that can combine with water, forming a strong acid, sulfuric acid. Of course, sulfuric acid can donate a number of protons. We also talked about NOx being formed in combustion reactions. The presence of nitrogen and oxygen forming NO2 can also react with water in the presence of oxygen to form nitric acid, another strong acid. And just like any acid, that molecule can contribute H plus ions and lowering the pH of the rain even further. Thinker Buddy question. What pair of substances reacts with water to acidify rain? A. Sulfur trioxide and ozone. B. Carbon monoxide and nitrogen monoxide. C. Ammonia and carbon dioxide. Or D. Sulfur trioxide and nitrogen dioxide. The correct answer is D. It's our SOx and NOx compounds that are released into the atmosphere upon combustion, burning of coal, burning of fossil fuels, that will form these strong acids on reacting with water. This ends the second part of Chapter 6.